Why do we have to just measure the rate of change of a function with respect to x or y? Why don't we measure the rate of change of a function in any direction? Now, what we're going to do is try to generalize this partial derivative idea. Now, recall that the definition of the partial derivative of the function of two variables with respect to x at some point x0, y0 was given above by this formula. We're going to rewrite this definition a little bit. We're going to let this vector A represent the point at x0 and y0. And so whenever we talk about f of x0 and y0, we are just going to think of this as the function at some point A. This is a little abuse of notation, but you should get the point quite straightforwardly. When we see this x0 plus h and y0 that appears in the definition of that partial derivative, we can think of this as some vector quantity. We can split this up into two separate vectors, and we'll be able to write it like this. Now remember, h is just some scalar quantity that appears in the limit there. So this is going to be the vector A plus h, and this is just our standard unit vector I. So the definition of the derivative can be rewritten like this. We'll say that the partial derivative at the point A is a limit as h goes to 0, f at A plus hi subtract f at A all over h. Now you might ask, well, what's the meaning of doing this? Why do we care? This notation is going to help us understand how to generalize a partial derivative. Now remember that when we have a function of two variables, we can represent it as a surface in R3. If we're talking about a point x0 and y0, they will be located at some point here. The function will be defined right above it. When we have a partial derivative with respect to x, remember that we take y is fixed. This is effectively like saying, let's draw a plane that exists at y equals y0. And this plane, as always, will intersect our function, and there'll be some sort of curve of intersection. This thing right here, this is a line that's in the direction of the vector I that goes through the point A. I'm just going to write this down as follows. That line goes through this point x0, y0, and is in the direction of the unit vector in the x direction. This is the line L. So right here is the point A, and right here is some other point that we will just call vector x, and that has some x0 plus h and y0. When we talk about this partial derivative, we would like to determine the slope of the tangent line right at this point here. We are drawing this point x closer to this point A, and this limit above calculates how the function changes along that line. So the slope of the tangent line at the point A is simply the partial derivative at the point A. So that's the slope of that intersection curve. You can talk about the y partial derivative at some point x0, y0. The limit as h goes to 0, f of x0, y0 plus h subtract f of x0, y0 all over h. So just like before, we are going to let the vector A be this point x0, y0. We are going to let the vector j be the unit vector in the y direction. The input to the first function in that definition can be written as the vector A plus h times j. So if we write it out here, we'll have f of A plus hj subtract f of A all over h. If we are to visualize this, once again, we'll have our function, we'll have our coordinate axes, we'll have our point x0, y0. The partial derivative wants you to hold x equals x0 fixed. There's some curve of intersection right there. At this point, we are interested in the slope of the tangent line. This line right here, L of h, a line that goes through the point A, but it's in the direction of the y-axis. So this is a line in the direction of j that goes through the point A. It's a line that lives in this plane right there. So there's the line L. When we talk about the partial derivative, what we're doing is taking 2 points. So this is the point A, and we're taking some other point X that lives over here, X naught, Y naught plus H, and we are sliding this over. This is separated by some value H. And the partial derivative measures how the function changes along that line or right above that line. So it's the rate of change of the function f with respect to y above the points on this L of h. If we start thinking about partial derivatives in this way, we will be able to generalize it to any direction. And this idea of lines is going to be important. So it's going to help if we visualize this again. So let's take our coordinate axes just like usual. We'll have our function that lives here. There's our point of interest right there. And this will be our vector A that lives at x naught and y naught. We'll have some other vector that lives at some point x and y. Now we want to pick an arbitrary direction. So let's say that we are going to pick some direction that looks like this. And the direction is going to be along some unit vector in R2. Now remember, if it's a unit vector, that means its length has to be 1. In a moment, we'll talk about why we want that length to be 1. What we're going to do is construct a line along that direction. That line is going to be going through the point here at A, and it's going to be in the direction of this unit vector u. If I were to take the derivative of this with respect to h, I'll just get the unit vector u. So the length of this derivative is just the length of the unit vector, which is just a 1. Since this length is equal to 1, this tells us that this parameter is actually our arc length parameter. It actually measures length along the curve. And if you go back to the x and the y partial derivative definitions, you'll find that the same would be true about the length L prime in each of those. Those derivatives measured the derivative with respect to length along that curve. Now, if we were to build a plane, there's going to be some sort of curve of intersection right there. And what we want to do is simply measure the slope of the tangent line right at the point that we're interested in. So what we're going to do is define something called the directional derivative of f in the direction u hat. Now, what this is essentially us saying the following. We want to take the rate of change of the function at some point along the line that we defined above. So it's going to be at some point a plus hu subtract f of a all over h. If we're just talking about a function of two variables, this would be f of x naught plus ah y naught plus bh subtract f of x naught y naught all over h. I'm going to go back to the picture here, and essentially what we're trying to say is if you give me this point A and you give me some other point here x, I'm going to try to move closer to that location. I'm going to build a secant line through that point. And as the 2 points move closer together, I'm going to try to figure out what the slope of the tangent line is. It measures how the value of f changes with respect to length above the line of points given by this L of h. And these points are just points along the line in the direction of this u hat. So this is the definition of our directional derivative. Now, of course, we need this limit to exist. And we want to know, when does this directional derivative exist? And how can we calculate this without using limits? So what we're going to do is try to come up with a computational version of this. As always, if you're interested in coming up with a shortcut formula or some conditions, what we need to do is go back to the definition. we are going to assume that this function that we've got, f of x and y, is differentiable. And we're going to assume it's differentiable at x naught, y naught. And in a previous video, we talked about the definition of differentiability. There's going to be a limit as some point x, y approaches our point of interest. F of x and y, subtract f of x naught, y naught, subtract these partial derivatives at the point we wanted, times x minus x naught, subtract fy at the point we were interested, y minus y naught, and that whole thing was divided by x minus x naught squared, y minus y naught squared. And it wasn't just that this limit existed, this limit equaled 0. For our directional derivative, we are interested in a very specific set of points x and y. We are talking about points that live along this line, a plus h times the unit vector u. So that means x naught, y naught plus h times some a and b. So if this is our point A here, we are building a line this way. And here's our other point that we're going to call x. Now this point is x naught, y naught. And this point here is x naught plus ah, y naught plus bh. This thing right here can be simplified. So here, if I were to go x minus x naught, I'm hoping that you can see this is x, this is y. This is going to give me x naught plus ah, subtract x naught, which is just ah. Y minus y naught is this expression minus y naught, which is just bh. And then that means that this entire expression here, the thing that appears in the denominator, can simply be written as ah squared bh squared, which is just going to end up giving me h squared, a squared plus b squared. This is the absolute value of h times the length of this unit vector. Well, I already know that this unit vector is 1. So all that does is it simplifies down to h. As the point xy gets closer to x naught and y naught, all that means is we are sliding along this line here. And that means that the distance between them, which we've already found, this is the distance between the points, xy, x naught, y naught. That distance is just the absolute value of this separation h. What this is going to tell me is that this h goes to 0. So I can rewrite this entire definition as follows. It's going to be a limit as h goes to 0. Upstairs, I'm going to have f of a plus h in the unit direction here. Subtract f of a. Now, the other thing that's going to happen here is I'm going to have a vector of partial derivatives that are evaluated at this point a. And as we talked about when we came up with this definition, we are simply going to take a dot product of that with this expression here. Now, I know that this limit has to be 0. This expression right here we're going to call grad f at a, so the gradient there. We know that this is simply ah and this is simply bh. We'll have f of a plus hu, subtract f of a. All of this is over absolute value of h. Subtract grad f dotted with the vector ab with this factor of h in the front all over that. And I know that this limit has to exist and this limit has to be 0. Now, since the limit exists, I can apply the limit laws. And if I can apply the limit laws, then I can get the following. I'll have the limit as h goes to 0 of this expression right here, subtract f of a, all over absolute value of h, subtract the limit as h goes to 0 of grad f at the point a, dotted with this unit vector u, multiplied with h over its absolute value. And that limit has to be 0. Regardless of whether h is positive or h is negative, This expression here is just going to give me a plus or a minus 1. There's only going to be a sign change difference. And that allows me to do one more rewrite. The limit as h goes to 0 of f of a plus hu subtract f of a all over h is then equal to the gradient at the point dotted with this unit vector u. This thing right here is the directional derivative of my function at the point A. So this directional derivative exists if f is differentiable at the point x0 and y0, and you can compute the directional derivative simply by finding the gradient of your function at the point x0, y0 and dotting it with the unit vector that represents the direction you're interested in. So this is a very, very, very convenient result. This special vector is called the gradient vector, and it's the vector of partial derivatives of your function at a given point. Now remember that this directional derivative is the rate of change of your function f with respect to length in the direction of this unit vector u. So let's take a look at an example. If my function is given by this equation, 1/4 x squared plus 2y squared plus 2, this is a paraboloid. And let's talk about this unit vector, 1 over root 2, 1 over root 2. If you wanted to talk about the length of u, it would simply be 1 over root 2 squared plus another 1 over root 2 squared, which is just root of 1/2 plus 1/2, which is the root of 1, which is 1. It is, in fact, a unit vector. So to try to illustrate what's happening, let's talk about a picture. So it's a paraboloid that's opening in the z direction. It's shifted vertically upward by 2 units. We are interested in x0, y0 being the point 3 and 2. And so that means somewhere over here is the point 3 and 2. And what we're doing is talking about the function at that point. We are building a tangent line. So the direction that we're going to talk about is given by this unit vector u that points this way. And essentially we are just tracing this up and saying right above that line, talk to me about how the function is changing. There is some curve here. There's a rate of change of this line. So the directional derivative is the gradient of the function dotted with u. The gradient of the function is simply the partial derivatives in each of those directions. So that means I need to take the x partial derivative of this expression. This is going to give me an x over 2. The y partial derivative of this expression. This is going to give me a 1/4 times a 4y, which is just y. So the gradient of my function is a vector. That's in terms of x and y. So the gradient of my function at 3 and 2 is simply just the vector 3 over 2 and 2. So the directional derivative of my function is then going to be the vector 3 over 2 and 2, dotted with the vector 1 over root 2, 1 over root 2. 3/2 over root 2 plus 2 over root 2, which is going to give you 7/2 over root 2, which is approximately 2.47. Now, if I scroll back up to the picture, what this is saying is that if I were to draw a curve of intersection, there is going to be a tangent line right there, and the slope at that given point is approximately 2.47. The directional derivative can easily generalize to any function that has more than 2 variables. So let's say I wanted to talk about a function with several variables. Because of the way that I defined it, everything can be extended to R3, R4, a function of any number of variables that you'd like, and the formulas will still be the same. We will still have the same limit definition of a function of however many variables you'd like, pointing in the same direction here, and it would still be computed by the gradient vector dotted with your unit vector u. So it doesn't just have to apply to 2 variables, it can apply to 3 or more.